I have, let's see here, anything else to show you? So here's how I prove the here's how I prove the regular Stokes theorem, and I think the proof of the generalized Stokes theorem is somewhat similar. What I do is I basically find a triangularization of the surface. All right. Well, I mean a polyhedrization. I don't know what you're gonna call it, but if you think about this, if I had like a hemisphere, right, I could approximate the hemisphere with a kind of jagged cap like this, right? And think about it, the more faces I take, right, the closer I can get to an actual hemisphere, right? And so you can imagine this as a sort of approximation procedure as a means of calculating an approximation of the integral over a hemisphere by instead integrating over the corresponding, if you will, triangularization. But the thing is, I can calculate this integral on any one of these faces, because if you parameterize the surface integral, this just becomes a two-dimensional integral of the curl. And what this is exactly the terms that you'd face in Green's theorem when you sort through the variables. So I simply apply Green's theorem to each face, and then I add them together. And because of the way that the boundaries are situated, the stuff on the edges cancels. So this is my proof of Stokes' theorem, basically, is just to prove it on a face and then add all the faces together. And then like interior faces, they get squished to nothing.
Is that what you were talking about with doing it on one chain?
Yeah, I think that the one-chain integration idea is the generalization of this. It's better than this, of course, but... And then... I also have just a gory proof of of Stokes' theorem by just straight calculating it for a, like a graph. So here's the calculation of Stokes' theorem for a graph which has the form z equals to a function of x and y. So to calculate Stokes' theorem, I have to calculate I compare the flux integral of the graph to the flux integral of the curl with respect to the graph to the line integral of the vector field around the four edges. And like the details of that are here. And so like the flux integral leads you to this. And when you do the integrals around the edges, it's always involving basically like fundamental theorem of calculus is always the detail. That if you get down into the nuts and bolts of it, it's the orientation of the edge paired with the fundamental theorem of calculus. That's how we actually prove Stokes' theorem explicitly. And this is just in a particular case, of course. But all right. Anyway, enough calculus 3. I just wanted to show you guys. But I found something I want to show you. Don't rickroll you? Again? I would never.
We got rickrolled in our class the other day.
Really?
What? Class rickrolled.
Really? That's beautiful. I like it a lot. I found something. I was trying today to work on some things, and then I got distracted. But so I'm still not quite done formulating my thoughts on what I was going to show you guys. But here's sort of the first fruits of some of my thoughts, and this may be as far as I ever get, so enjoy it. But I think we can get Hodge duals of other coordinate systems from the determinant of the Jacobian for the system. So do you guys remember from Calculus 3, if we had x equals to rho cosine theta sine phi, and we had y is equal to rho sine theta sine phi, and z is equal to rho cosine phi. I mean, nothing too controversial here, I think. What was the Jacobian for this? Do you guys remember? So here's the thing. If you calculate dx, wedge dy, wedge dz, you can calculate that is the determinant of this thing. So you got your x rho, y rho, z rho, x theta. Oh, my bad. I'm supposed to do x phi, y phi, z phi. I gotta, my inclination is to put theta first, but it's wrong. The proper orientation of the spherical coordinate system puts phi first, then theta. The reason being, if you remember how these things work, this would be like a theta hat, and phi hat would be directly down, right? Because we're measuring phi like this, whereas we're measuring theta like that. So these are the unit vectors in increasing theta and phi. If I take phi hat and I cross it into theta hat, try again. So theta hat would go directly back here. Phi hat would go directly down here, right? Where would phi hat cross theta hat go? Minus rho hat? Don't say that. No, it goes this way, which is rho hat. That is why I'm putting the order of the parameters here, rho, coordinates rather, rho, phi, and then theta. All right? Many times I have done the opposite. I have done rho, theta, phi, and done a page of calculus only to get minus what I wanted and go, ah. Now, in my defense, it's partly because I was raised by physicists, and in that context, the meaning of theta and phi is switcherooed. And that'll mess with you. That'll mess with you. But the thing is, this, I'm owing you a d rho, wedge d phi, wedge d theta. All right? This is one aspect of the pullback. Right? Like the pullback of dx wedge dy wedge dz to like rho theta, rho phi theta space is that. What is that though? I don't want to work it out, guys, but I mean, we worked it out in Calc 3 for sure. It is rho squared sine phi d rho wedge d phi wedge d theta. You maybe you recognize this as the necessary multiplier for setting up spherical integrals, right? So I had a thought, which is, hey, if I understand Hodge duality, then I can take Hodge duals of the spherical basis as well. Like, for example, what would the Hodge dual of d rho be? I say, because you can write this as d rho wedged with rho squared sine phi d phi wedge d theta, right? And this is, you know, my form wedged with my potential Hodge dual of the form, and it's equal to the volume form. That's the volume form. This means that the Hodge dual of d rho is rho squared sine phi d phi wedge d theta, yeah? Do you guys agree? So, one of your homework problems, you had this here omega, which if I recall correctly, and I do, is x dy wedge dz plus y dz wedge dx plus z dx wedge dy. all divided by x squared plus a y squared plus a z squared to the 3/2 of power. The Hodge dual of this, right, under the Euclidean metric is simply x dx plus y dy plus z dz over x squared plus y squared plus z squared to the 3/2, yeah? So, if I have so I've got F, right, is a mapping from R3 to R3. Don't mind the coordinate defects. And let's see, I'm pulling back. So I guess I'm going from X, Y, Z space, right, back to rho, phi, theta space, right? So you guys tell me, what's the pullback under F of the Hodge dual? I'll use a regular star for that if you guys don't mind. Hodge dual of omega. That's just a fancy way of saying, rewrite this in spherical coordinates. Notice that rho squared is x squared plus y squared plus z squared. So 2 rho d rho is 2x dx plus 2y dy plus 2z dz. In other words, the denominator of that is straight up rho d rho, and the denominator maybe, rho cubed, yeah? So lo and behold, we have d rho over rho squared. So, what is the Hodge dual of the pullback of the Hodge dual of omega?
This is natural mapping. This is natural.
Sine.
Yeah, I mean we got apparently the Hodge dual of 1 over rho squared, right? Times d rho. 1 over rho squared we can leave out here. And then we got the pullback of d rho. But the pullback of d rho, we calculated that earlier. Rho squared sine phi, d phi wedge d theta. So we got ourselves a sine phi, d phi wedge d theta. AKA the pullback of omega. I don't know. But it's true here because you calculated it the other way and you got that. And it was not that easy. Not that bad?
It wasn't hard, it was just...
Tell me it was impossible. I want to hear it was really, really hard.
Only
My
because
brain
I
was
made
really
one
hurting if I
mistake
just
and had to
remembered.
find out where the mistake was.
First or wrong.
Wait a minute, I think whatever Preston just said I don't want to listen to. That's a good question though. I'm not sure. I want to say that it holds, but I think the context has to be like we're talking about a form on a particular space and we're just pulling it back to the same space with respect to a coordinate system on the space. I'm not so sure. I'm not so confident this would work if I was actually working with a pullback between different manifolds or something.
So it has to be inversed.
Yeah, I think it has to be like a coordinate change pullback as opposed to like a pullback between manifolds that are genuinely like different dimensional or something. I'm not sure it would hold there. But this almost has to happen because the Hodge dual is defined in a coordinate invariant way. Not that we did that, but it can be. Yeah. Of course, it goes back to the question of how on earth do you define the Hodge dual properly, right? That seems to be a theme in this course. How would we make a proper definition of certain things, you know? Yeah. But, well, okay, like, all right, well, we're on this tangent. What's the Hodge dual of d phi?
Negative rho squared sine phi d rho wedge d theta.
I don't know if it's negative.
Ah,
Oh, never mind. It's not there.
so minus rho squared sine phi, what did you say?
D rho wedge d theta.
D rho wedge d theta, yeah.
Or you could do just rho squared sine phi d theta wedge d rho. Would make more sense.
Or you absorb the,
Positive
so rho squared. I do believe that properly appreciated, these can be used to, like, find the proper area form. Like, sure what I mean. Okay, so like the sphere, right? Well, of course, the outward orienting normal vector field is phi hat, right? Rho hat, rather. What's the area form on this? Like, we do sigma, it's, you know, this thing, you know? This is the proper volume form on the sphere, the unit sphere, with respect to spherical coordinates, right? If I want to, like specifically, if I have a 2 form out in Rn, I would, if I pull it back, well, I'm sorry, I'm not saying things correctly. Words. I don't know, there's more to say here. I'm not ready to say it yet. Like I said, this is the start of something I may never get to the end of, but I wanted to show you guys before I forgot. So, anyway. Thanks, guys.